So we'll see the core concepts of software designs. So software design is an activity and software design is also a product. So the goal, we have to create an optimal design to satisfy the requirements. So there are three levels in design process: architectural design, high level design, and logic design. So architectural design, as we saw previously, the architectural styles, pipe and filter diagrams. So we try to identify the components needed for the system and how well they interact, what is their relationship. So the components will be represented using the filters and the relationship, or the output from each components would be represented using the pipes. So this is an high level view of the system. High level design is module view of the system. So for each component, there are many modules and submodules, and we'll try to identify the modules and submodules and how are they going to be organized. And then we have the logic design. So we are trying to implement the identify modules. So we'll start constructing pseudocodes, algorithms to implement those modules which are identified. So architectural design gives you a high view of the system. High level design gives you the module view of the system, and logic design gives you the implementation view of the system. Okay. So in high level design, we can have a module, a function, a class, and then you will have a package, and then there are various ways to specify those module cluster. So design process can be top down versus bottom up design. So top down means it starts with the system specification, and we'll start to define the module to implement those specification, and then the subordinate modules, and then we treat each specified module as a problem, and we'll start implementing. But bottom up approach is like we start with the core building blocks, and then we'll start building the other necessary aspect. Mainly, we'll start with the back end and then create the front end. Or we'll start with the core functionalities and then we'll add the extended functionalities. Two examples I would like to give. One with the calculator. We'll first start with the core arithmetic operations, and then we'll start developing the user interface, and then we'll extend with other operations, other computational operations. The other example would be machine learning algorithms. We'll start with using to develop machine learning algorithms with the APIs available, and then we'll try to create a user interface to interact with test data or newly constructed data. So first we'll start with the backend algorithms, and then we'll start creating the user interface. So there are two key design principles. One is the abstraction, another one is the modularity. So abstraction means we are trying to provide only the necessary detail possible. So for example, in a car, we have brake, clutch, and accelerator. We press it and the car moves. If you press the accelerator, the car moves, and brake, the car stops. But we doesn't know what happens at the back end, and it is a black box for you. And it is very easier for you to interact with the back end system of the car. So abstraction provides only the necessary details, and it is used in all engineering disciplines. As I said, now is an automobile design. So we represent module as a black boxes, and we hide the detail that provide the external behavior. So the external behavior is like accelerator, and the brake is you're pressing that, and the car moves and the car stops. That's the external behavior. What happens behind the external behavior is hidden. Okay, so abstraction can be functional. It uses functions, or database uses classes and objects. Okay, so modularity means it is closely tied to abstraction concept, but modularity actually supports independence of modules. How well each module is independent, how well it is less dependent on other modules to fetch data. So it reduces the cost of testing, debugging, and maintenance. So in the next video, we'll see about two main design principle concept, coupling and cohesion.